And we are going. All right. Well, maybe we're going. Okay, there we go. Yes, today we're going to do a review of encryption. I assume that everybody here knows something about encryption. You've gotten this far in a computer science graduate class, you probably talked about encryption before. But I wanted to just go over it to make sure we covered all the ins and outs. And so I put together some slides, some of which I stole from several other classes and some I made up fresh. Just a reminder, Project 6 has been canceled. I've written Project 7. The TA is reviewing it. We're going to make sure it's a worthy project before we move on. If you did Project 6, I apologize. I know people were upset when I did a lot of work on Project 6, but I didn't think Project 6 had assignments that were realistic. Project 7 will be a little bit more realistic. It also will not involve the virtual machine. Okay, but let's talk about encryption and cryptography. Here's the basic concept of cryptography. The whole idea is you start with plain text. Plain text is just a bunch of bits. It can be text, a document, it can be graphics, it can be a program, whatever you want. Bits are bits. It doesn't really matter. You take that and you go into an encryption algorithm with a key. And that encryption algorithm produces something called ciphertext. So what's being shown here in the middle is ciphertext. And the ciphertext looks like a random bunch of bits, no real pattern to it. And then the ciphertext can go into a decryption algorithm along with a key, and out comes the plain text, which should be exactly as it was when it started on the input. So you can't see that. Oh, doggone. Okay. Excuse me, let's see if I can get some of these things to work. Oh, I know we're having challenges with these video systems. It's just not working at all. Okay, well, enough of that. Too bad. Okay. Back to it. Okay. People have been doing encryption and ciphers and this for years, for millennia, for thousands of years. There's the Caesar cipher, which is still used sometimes. It's very simple, but it was said to have been used by Julius Caesar. People sent messages and they didn't want other people to read them, so they had to encrypt them in some way. Of course, and I also have the other picture is supposed to be Sherlock Holmes. If you read any Sherlock Holmes novels, Mr. Holmes is occasionally involved in encryption. But if you had encryption in those days, computational efficiency, how hard was it to encrypt something and how hard was it to decrypt it was a very important issue because you had to do it by hand. Now we use computers and we encrypt things. We don't write them on paper. We usually put them into files and we send them across the network. So you can have data at all levels. You have data in motion, which represents data being sent across the network. And you also have data at rest where it's being stored. In both situations, you want to use encryption to keep it safe, to keep other people from seeing it. Basically, the way most encryption systems work, they rely on two concepts, diffusion and confusion. Diffusion is the idea that you spread information out broader than it used to be. In other words, if you imagine you start with bytes or characters, you start with a character, then that character is not represented by one character. The easy, like the Caesar cipher or some of the other ones, were character replacement algorithms. You take this character and you replace it with that character. And those are very easy to break. You see them in the newspaper. They have in the Greensboro News and Record, So every day they have a little puzzle, they give an encrypted quote, and you have to decrypt it. And they use one character for character. It's easy, it's not that hard to do. And so, but diffusion is each character's information is spread across a much broader range. In the AES algorithm, which is very popular, it encrypts 64-bit blocks. If you change a single bit in the input, the output will differ by almost half as many bits, and there's half the bits will be changed. So there's a wide diffusion of the information. Changing one bit doesn't change just one bit in the output, it changes half the bits, which is what you expect. And that makes it very difficult to determine what the input was. And then there's confusion. Typically, you'll do some algorithm on the input to change it. Exclusive OR is very popular. We've got the rat and the rabbit here from other semesters. I couldn't resist. I just, my favorite characters. There's no good reason for us computer science to know the details of encryption algorithm implementation. Yes, I'm not going to teach you how these encryption algorithms. There's no reason to know that. I mean, I know other classes spend a lot of time on that, but you know how to. You have to know how to use them. You don't have to create them. You don't want to create your own. You want to use what exists and use it correctly. Okay, and I've got my first clicker question of the day, and I think if it all goes well, there should be a poll. Yes. So you should be seeing the poll right now along and see it out there. So we've got the, you have your paper? Oh, you're in luck. I have one paper left. Oh, it's a big one. It didn't print well. So okay. So the online people can click away as they see fit. Let me get my phone app. And okay. All right. Figured out the answer. Let's see if I can get this to work. Clicking more buttons than you'd imagine is necessary. Okay, put your answers up there if you would. And go on. Okay, got them both. That's quick. Okay. All right. We have an A and a D. Everybody voted for we have A and D and 3 B's online. All right. What is the answer? The answer would be B. Yes, the answer is B, one-to-one mapping. Think about this for a minute. Okay, one-to-one mapping means you have plain text, and for each plain text, there is one and only one ciphertext for a given algorithm. There's different algorithms be different encryption methods, but for given algorithms, what do I? Because you have to be able to go backwards. You want to be able to decipher it. So it isn't one-to-one. If it's many, if it's one-to-many, then how do those many go back? And usually, since you allow input of every possible combination of bits, so if you have a byte, there's 256 different combinations, and all possible ones may be input. You have to go one-to-one because you have to be able to get back. Okay, so the answer would be C, one-to-one. Okay, there are various types of encryptions, and generally we divide them in different categories. You can say there's symmetric key, sometimes called secret key, and asymmetric key, sometimes called public key. I want to say right now that because it's public key does not mean it's less secret than secret key. Some people say, oh, you don't want to use public key, you want to use secret key because the key is secret. No, secret key means you use the same key to encrypt and decrypt, whereas public key, there's a different key to encrypt and decrypt. Here's a picture that describes it. Okay, you've got your plain text on the left, and you want to send it. Again, in this case, we're transmitting it, but it doesn't matter. We could be putting it in a file and getting it back. You use a key that encrypts it, and then you send it across the network, and you use the very same key on the other side. So the sender and the receiver have to share keys somehow. you have to give the other person the key to make sure that she has the right key in order to decrypt what you're going to say. There's various ways to talk about sharing the keys. We'll talk about some in a minute. You know, the traditional way was you put the key in a pouch and you gave it to a Marine who went across to the other ambassador and gave him the pouch. But, you know, that works. There are other ways to do it. There are symmetric key algorithms that use the same key to encrypt and decrypt. DES and AES are very popular. AES being probably the most popular one right now. And then there's asymmetric. Asymmetric, or public key encryption, has two different keys. You use one key to encrypt the data and then a different key to decrypt. And I might point out that the RSA algorithm, which is the very popular one that's used, can go in both ways. You have a public key that everybody knows, that you can put out on key directories, and people can look up and everybody can find out your public key. And then there's a private key that only you should know. That should be kept secretly in your system, and only you know this, the private key. And you can encrypt with the public key and therefore decrypt with the private key, or the other way around. You can encrypt it with the private key, and anybody can decrypt with the public key. And you might say, oh, what good is that? Anybody can decrypt it. You know, okay, you encrypt it with the private key, anybody can decrypt it with the public key. That's true, but they know when they get it, they can decrypt it with your public key. It must have come from you because only you know the private key. So we've got standards for encryption. We've got the data encryption standard, which is old now. We have the advanced encryption standard. We have other algorithms, RSA, Diffie-Hellman, that are all well published. Well, some people think, shouldn't you keep them secret? Why do you want to use an encryption algorithm that everybody knows? Well, because the big thing is, if I'm going to use encryption, I want to encrypt something, and then you need to decrypt it. So both you and I need to know how to do the algorithm. Need to know what the algorithm is and how it works. So we have to share that. And again, if you want to share with a large group of people, everybody has to know how the algorithm has to be able to implement the algorithm so that they can decrypt what I send them or encrypt what I receive. So you need to share these up. Also, a good algorithm relies on the key. If you don't have the key, you can't get the data. In other words, you can't decrypt it without the proper key. Knowing the algorithm doesn't help you much. You have to have the key to do it. And also, many of these, well, all these well-published algorithms, the ones that are standardized, have been used for a long time, and experts have looked at them and determined that they are safe. Do not try to create your own encryption algorithm. Learn to use existing algorithms better. Do you think you're better than the experts? Okay, we got another clicker question. See if you're paying attention or if you're awake. Take a look at that for a minute. All right, let's try again. Okay, put your answers.
So,
Yes.
Professor, is there a poll for this, or we just
Yes,
put it in?
I'm sorry. I forgot to start the poll. I'll give you just a minute here. Come on. Stop sharing. We need the right. There it is. Okay. There's the poll. I apologize. I should have started that earlier. Okay, you all see the poll now. Okay, you're answering good. And here in the live stream, put your answers up if you would. Oh, doggone. Okay, there we go. It sees you and sees you. Okay, great. Okay. I apologize. Okay, we have, somebody just changed mine. 3 A's, 2 B's, and a 3 A's, a B, and 2 C's. Okay, we're going to end poll. Yes. Well, plus so it's 3 A's, 2 B's, and 1 C. That's unfortunate because the answer is B. I know this is kind of a trick question because we didn't talk about compression. I don't know if any classes talk about data compression. But okay, when you encrypt something, it takes the text or whatever it is, it has some sort of structure to it, and it converts it to a file that looks just like random bits. Random bits are extremely difficult to compress because you don't know what it is. Compression works by looking at the likely next byte or next bit in the data. For instance, think about when you're texting a message or writing email. You're texting a message, you go along, and my system, as I write something, gives me a suggested word. I put a character up there and it thinks, you want to send this word. And frequently, yes, I want to send that word. So it shows me 3 choices. So a really simple encryption algorithm would be, okay, here's the beginning letter, and then I took this choice on my phone for texting something. So I could go, okay, I typed in a B and I want to take the 3rd choice. And then I typed in a F and I want to take the 1st choice. Or you might say, well, none of those work. So you put another character in, and it gives you another bunch of choices. And so, yes, you could encrypt things that way. There's a lot of structure in English things. So compression, looking at the structure of things, following that compresses it down so it's much smaller. So you want to compress first and then encrypt, because if you encrypt it, you convert it to just random bits, and that does not encrypt very well. Okay, trick question. Didn't talk about encryption, but just couldn't resist. I like that question. Some people don't know the answer. Okay, encryption performance. All right, there are multiple encryption algorithms. And they don't all run at the same speed. The RSA algorithm, which is the popular asymmetric one, the public key algorithm, that is significantly slower than AES. DES and AES are easy to implement. AES can be pretty well done in software. Your Intel processor and your AMD processors have hardware in them that since for the last, I don't know how many years, the Intel processors have instructions to do AES encryption and decryption. It does a AES step in the AES algorithm, which we're not going to talk about the details. There's many repeating steps. You have to go through 10, 12, 15 iterations of it, and the instruction does an iteration, but it does it in one hardware instruction, so it runs pretty fast. And since you do these, you can pipeline it and get a lot of this done very quickly. Yes, so again, hardware to do it, it runs pretty quickly. RSA is not fast. RSA is considerably slower. RSA takes a lot more computing power to encrypt things. The keys are larger. Keys are sometimes 2 or 4K, whereas your AES keys, well, it varies. It can be 64, 128, or 256 bits long. Oh no, let's see. 128, 196, and 256 bit long. The big one is 256, the small one is 128. So big keys, 128-bit keys, much smaller. We'll talk about that in a minute. And then there's some people use hybrid. I mentioned hybrid systems use both asymmetric and symmetric key systems. As you remember, for a symmetric key, which is like AES, they're very fast, but you have to share keys. I have to give my key to you so you can do it. Well, they do that in the transport security layer, which uses a hybrid encryption. It's used a lot. It's the security in HTTPS. When you have an HTTPS website, the S means it's secure, means the information is encrypted, is getting sent over the web, and they use the TLS, or transport layer security, to do that encryption. There was a similar system, secure socket layer, SSL, that was used earlier, and that was deprecated back in 2015. Deprecated meaning that it was recommended that nobody use it, that someday they're going to remove that system. TLS is used by a lot of systems, web, IP, a lot of systems that send information over the web use the transport layer security to encrypt things because it works pretty well. basically, here's how it works. The client's going to connect to the servers. The client sends a request to the server saying, hey, I want to do a encrypted, I just want to just HTTP, I want to do HTTPS, I want this to be encrypted. Here are the options. Obviously, here are the algorithms that I'll use, other options that are available. The server picks the hashing algorithm, the Cypher algorithm that it wants to use, and sends its digital certificate to the client. The client then, once it has the digital certificate, checks to make sure that the server is who it's supposed to be. They have proper certificate claiming to be that, for that server, and then makes a random number that they're going to use for an AES key and sends it to the server, who then uses it. Here's a diagram. Let me explain it with this diagram. Oh, if I could annotate things. Oh, I can't seem to get anything to work today. Sorry. Oh, well. Don't know why it doesn't work anyway. Okay, well, beginning when you first start TCP connection, the client tells the server, I want to connect. The server says, okay. And then the client sends a message to the server saying, I want to do HTTPS. Here's the algorithm I like. The server picks the algorithm, sends its certificate back over to the client. The client says, okay, let me check that certificate. Are you really who I hope you are? And then specifies the product, makes up a key, and then sends it off to the server, who says, okay, I like that key. Here's what we're going to do. And it sends that information back to the client. By this time, both sides have an AES key. The AES key was made by the client, sent to the server, which is encrypted using the public key of the server. So the server sends its certificate. The certificate contains the public key of that server. So now the client can encrypt the AES key using the public key. Send it off to the server. Only the server can decrypt because only the server has a private key that carries that public key. And now it has the AES key. Now both sides have an AES key that they delivered securely. And even though RSA is not terribly efficient, if you're only going to encrypt 256-bit, or that 32-byte message, it doesn't really matter. It's not that inefficient. So you can send it across, get the other side, and then decrypt. And once you have it, once you shared the AES algorithm or AES key, then both sides can send information encrypted with AES, and it's much more efficient, does it very quickly. So starts off just sending information, sends certificates, and then sends information encrypted in the public key, since the key encrypted with the public key, and so both sides can get a private key. Obviously, well, it should be obvious, the longer the key, the harder it is to defeat it. If you imagine a key that's only 2 bytes long, well, 2 to the 2 is 4. There's 4 possible combinations. Well, you could try all 4 possible combinations and see what one seems to work. And in most cases, that would be pretty easy. So if you want to try by brute force, and there's n bits, you have to try 2 to the n guesses. And of course, if you're lucky, you should get the answer in about half, well, on average, half the time, which should be 2 to the n minus 1 guesses. Now, with AES and DES key, being the symmetric keys or the private key systems, almost any bits can be a key. That's not so with RSA, because RSA requires one side to use an algorithm to make the key. So you can't just use any bunch of bits. You have to go through an algorithm to make the keys. So therefore, they're larger. Whereas with AES, almost any random bunch of bits will do the job. Not so with RSA. DES, which is an older algorithm, started off in the 70s, I think. Data encryption standard uses a 56-bit key, which is far too short. People have shown that they can decrypt that relatively quickly now. Computers have gotten faster, algorithms have gotten better, and people can decrypt DES pretty quickly. What? What? I'm just leaving. Okay. Well, anyway, they can decrypt DES pretty quickly, not, in minutes, but maybe in an hour or so, you can decrypt with the computers we have today. When you have big computers, particularly big parallel computers like the government might have, you can do it pretty darn quickly. Some people thought that maybe the government had an impact in saying DES shouldn't have a big key so they could decrypt it, but I don't know. There's triple DES. Triple DES uses DES 3 times to encrypt something, but it only uses 2 keys. I can't remember exactly how it works, but it's something like encrypts it first with key 1, then goes to the algorithm, decrypts it with key 2, then decrypts it with, encrypts it with key 1. It's but it only uses two DES keys. So even though it does 3 encryption phases, only uses 2 keys. So 2 times 56 is 112 bits. The AES algorithm, which is much newer, than DES, it was generated about 10 years ago or so, is 128.92 or 256 bits in length. Now RSA, of course, because the keys have to be created by an algorithm, they can't be just any random bits, or have to be much longer to be secure. And they're often 2K, sometimes now even 4K in length, so much longer keys. So far, nobody's found a way to compromise the AES algorithm. At least they haven't told anybody. Snowden, the fellow who released a whole bunch of NSA documents to WikiLeaks a few years ago, claimed that NSA was looking into techniques to defeat AES. Well, I'm sure they were. Isn't that their job? I mean, gosh, as a taxpayer, I hope they were. I hope we can't do it and tell anybody, but yes, I would expect that they were doing that. People are working, cryptanalysis people are working on how to break AES. Somebody did find a way to make it, break it 4 times faster. Well, 4 times faster, yeah, okay. But they also said if it requires storing 2 to the 88 bits of data, which they pointed out in the paper they wrote, that's more than all the data and all the computers on the planet. So that's kind of a tough call. Okay, so here's another clicker question, and I do have a polling question for this one. Okay, what is 1/4 of 2 to the 256? Okay. Get your calculators out or something? Should be able to do this arithmetic. Okay. So without trying to convert it, I suppose your calculator might be able to tell you, if you ask it for 202 to the 256, it might be able to tell you what that number is. And then you can divide it by 4, then you take the log base 2 of it and calculate that. It might work. Or you might just know. Okay, everybody think we know the answer? All right, there's people online. Let's see some numbers. Okay, got you, Mr. Hernandez. We've got to turn it the way you like. We got one over here. Okay, got them all. All right. All right. We have 6 responses, 5 A's and 1 D. Well, whoever did the D, you got it. That's the answer is D. Yes, sorry to say, the answer is D. Okay. Go away. All right. Yes, you can get the answer. 250 divided by 4, which is 2 to the 2, and that's just division. It's just subtraction of the logarithm. So it's 256 minus 2, which gives you 254, which is, by the way, about 1.6 times 10 to the 76. Still a really big number. No computer today can brute force this in your lifetime. What about it? Brute force by a quantum computer? Well, the RSA algorithm is said to be vulnerable to quantum computers. AES is said to be quantum proof. Besides, you ain't ever going to see a quantum computer in your lifetime. What? Contrary to what other people in the university are doing, you're never going to see a quantum computer. That's the Ken Williams prediction. Don't put your money into quantum computers. It ain't going to happen. Your opinions may vary. That's mine. That won't be on the test. Okay, but yes. Okay, yeah. Guys got to go back to take your math classes. There will be no math on the test, but you ought to know that. Okay, now, just because you have a good encryption algorithm, if you don't use it correctly, it isn't going to do you any good. You have to use it correctly. And of course, it has to be implemented correctly. Don't implement it on your own. We have all sorts of encryption libraries to use. Use a good library, and you won't have a problem. But you have to use it with the proper encryption mode. Let's talk about encryption modes. There are many ways to encrypt, not just to encrypt, but to also what mode to use. The basic is a block mode, where you encrypt one block of plain text with a key, and you get a block of ciphertext. And then there's stream encryption. But in block mode, the thing that's important here is that if you have the same block, say block 2 and block 3 are the same, then the ciphertext block 2 and block 3 will be exactly the same. And that gives the cryptanalysis people a lot of information. So they know, oh, the second block is the same as the third in the plain text. So again, it's pretty simple. You take plain text into the encryption algorithm with the key, and you get ciphertext. Simple enough. This is a very interesting picture that I found online. That they took a image, BMP image, and encrypted it with electronic cookbook. Electronic cookbook, ECB, is the block mode of encrypting things. I don't know why it's electronic cookbook, but that's the term they use, ECB. And you can see, if you look at the picture, you can kind of see the image in there. Because, of course, the background is white. When you encrypt a block that has the background, it comes to ciphertext that looks the same thing. When you get to something black, it has a ciphertext that looks the same. So you can see the image, even though it's encrypted with AES, which is very difficult to decrypt, you can still get the concept. So using good encryption requires using it properly. Properly means not using electronic cookbook, but using one of the stream-oriented encryptions. And we'll show a couple of stream-oriented. The stream-oriented encryption, each block that is encrypted is then used to encrypt the next block. This is a very popular one, cipher block chaining, CBC. Here they can, ECB is electronic cookbook. CBC is the cipher block chaining mode. And you can see here, we start with an initialization vector, talk about that in a minute, and plain text, you exclusive OR them together. This little box with the plus and circle, that stands for exclusive OR. And so you exclusive OR it, and then you take that exclusive OR result and you encrypt it with, AES or whatever you want to use, and that gives you some ciphertext. Then you take that ciphertext, the first block, and you encrypt it with the plain text of the second block, encrypt that, XOR that, and then you take that exclusive OR first encrypted block to the second plain text, encrypt it, and get you the next one. And that one again is exclusive OR, the next plain text block, and encrypted, so forth. So any change, even if these two blocks, second and third block, are the plain text are the same, well, this one, you take this up and you exclusive OR with that, so what's being encrypted is going to be different because this is not that. And so any change you make in the plain text, if you make a 1-bit change in the plain text, all the following blocks will be different. And this can be decrypted relatively easy. Here's the decryption, just about the same. You take the initialization vector, the same initialization vector you used previously, and then you decrypt the text, exclusive OR, and you get the plain text, and then of course that ciphertext is used, the next one, and so forth. So again, it streams down. You use the results from the previous one to get the next block. Now they use an initialization vector. Initialization vector is basically just some sort of dummy ciphertext to start the process, because as you can see, each one requires some sort of, it gets input from the previous stage. Well, what does the first stage do? It gets input from the initialization vector, which is just a bunch of bits. Typically, just a random bunch of bits. That's the same size as the plain text blocks. Typically, it doesn't have to be kept secret. You will append it at the beginning of the data or send it along with the information. So the first, say, 256 bits or 32 bytes is an initialization vector. So you get it received, you take that and use that as initialization vector. Now, every time you send the data or every time you encrypt it, use a new initialization vector. Again, it's just random. So you make yet another one and you send it. That way, every time you send, even if you send the same information, because you use a different initialization vector, it looks different. In other words, the cipher bits that are sent across the network are different, even though you're sending exactly the same information, exactly the same bit for bit. It looks different to somebody trying to figure out what it is because the initialization vector is different. Now, of course, you have to keep the initialization vector with the ciphertext. Append it to the beginning, send it along. If you're storing it on a disk, you'll have to also keep that. That can be something of a problem if you have a system that encrypts the data and then stores it back in exactly the same place where it was. Well, now it's a little bit bigger. That can be a problem, but usually not. You can, usually as you read it, you edit a new file and just change the file and pointers and it all works. Now, even though I say you don't have to encrypt the initialization vector, you may wish to protect it to make sure that it hasn't been changed, that somebody hasn't changed it. Mac, we'll talk about those in just a minute. They can be used to protect it. Now, of course, Cypher blockchaining is not the only stream-oriented one. Another one is Cypher Feedback. This is, again, in this case, you encrypt the initialization vector, exclusive OR to result with plain text and get your ciphertext that feeds and goes through. So again, that's slightly different than this, Cypher block. But they both work. You can use either one. It's interesting that the decryption of this uses the encryption algorithm. You never, in other words, assume you're using AES to encrypt this. You use AES to encrypt it, and you use the AES encryption to decrypt it. There's another one called the Gallows or counter mode. And this is interesting. This has the advantage that it's easily parallelized, which is useful if you want to do a lot. Encryption can take a lot of processing. In fact, people have found if you have a server, most of the server's CPU time can be spent doing encryption. So it is computationally intensive. This one, you can do it in parallel. It's really a simple concept. Okay, you start with initialization vector, whatever. And that, assume that's a counter. Think of that as a great big number. And then you increment that number. So now you have this number, you take that number and you encrypt that number, and then take the result of the encryption, exclusive OR with the first block of plain text, and that gives you the first block of ciphertext. Now for the second, then you take that counter that you had, you increment it again, and now encrypt the incremented one, because remember, with AES, if you change this one bit, even though we're only, if you're going from like number 2 to number 3, you're only changing one bit, but the result of the encryption will change about half the bits, and then you exclusive order that with plain text. So, even though here it shows it going from 1, you can imagine if you had 8 processors, the first one always does it with counter 1, and then they add 8 to the counter and do it again for the next 8, for the 8th block. You can do it in parallel. So it works well. This is the encryption algorithm used by Zoom. Whenever somebody says we've got this is the Zoom ID and here's the Zoom password and encrypts it, Zoom uses this encryption system. Just to get distracted for a minute, Zoom, when they first came out with their encryption, they go, oh, we offer end-to-end encryption. Well, they didn't offer end-to-end encryption. That was not true. That was their big claim, and they claimed it in their documents and several times. But it turns out what they did is they encrypt Zoom. When you have a Zoom like we're having right now, my computer is connected to the Zoom server. Your computer connects to the Zoom server. Well, the connection between my computer and the Zoom server is encrypted. The connection between the server and your computer is encrypted. But they're two different encryption. As it goes to the server decrypts it with my key, encrypts it with your system, and sends it to you. So in fact, the server sees it unencrypted. This concerned people because Zoom is a company that originated in China. And so people were worried that the Chinese would be able to see everything that we did on Zoom. But I'll tell you, if the Chinese want to watch my class, they're welcome to do so. Anyway, people got upset. They sued, and Zoom agreed to pay $85 million. They didn't pay it to me, and they stopped claiming they did it. Okay, and they claim they also gave user data to Facebook and Google, although I don't know about that. Anyway, $85 million, some money. Okay, cryptographic hashes. In addition to just scrambling up the data so you can't read it, another thing you want to do is ensure that it came from the same person. You want to, encryption provides the ability to keep the data from being seen, but you also want to protect the data from being changed. You want to keep its integrity. So what you can use cryptography for that. A hash is a calculation over all the bytes of a file. A really simple hash is simply to sum all the bytes. Look at each byte of the file as being a 8-bit number and add them all up. Don't worry about overflow. You can add them all up to a 32-bit value or a 64-bit value, and fine. And then that's the hash. That's a very simple hash, and not really very effective. There are many that are much more effective. But anyway, you want something that's relatively easy to calculate and is unfeasible to go backwards. So given a hash number, you cannot create a document that will create that hash number. Now, a little logic will tell you that if the documents are 1 megabyte and the hash is 160 bits, there's got to be, that's a many to one mapping. There's got to be lots of documents that go to. But it turns out there's no known way to go backwards. Given a hash, nobody knows how to make a document that creates that hash. That's called a one-way function. To be honest, there, as far as I know, none of them are provenly one way, but they believe to be one way. Nobody has a way to go backwards. Every now and again, somebody finds a way to speed up the stuff. They can make it 10 times faster, which usually still means it takes more than a lifetime to resolve. So again, if you want to send data across the web, you can create a hash, append it to the data, and send it across. And then the other side, when it gets it, you can create the same hash in your data, compare it to the hash it got, and see if it's the same. Now, of course, if you just send it like that, some sneaky attacker along the way could get your file, change it a bit, recreate the hash, and send it. So typically, after you create the hash, you encrypt it with your encryption system. You only encrypt the hash. And then you send the hash along. The other side calculates the hash, decrypts the one they sent, and see if they match. Somebody along the way can change the file and recreate the hash, but they don't know how to encrypt it with your key. Assuming you don't know your key. There are several popular hash algorithms that have been out there. SHA-1 has been out there for a long time. What is that? That's almost 28 years. Wow, that's a long time. And it generates a 160-bit one. There's SHA-3 and SHAs, and most of them now have things like SHA-256, SHA-512, and they are more secure. And of course, they create larger hashes, more bits. There's something called Blake 3, which is another efficient popular hash. It's got the advantage of being parallelizable. Hashes are also used for keeping passwords. Typically, you do not store the password text in a file. So if you have a system where you log in with a password, you should not be storing that password in the file. Instead, when you get the password, you run it through the hash. Then you get the hash and you store the hash in your database. And when somebody tries to log in, you take the keys that they entered, run it through the hash algorithm, get that hash result, and compare it to the hash of what you have in the file. If the two hash values match, then they probably had the right keyword. Now, again, it is possible, but nobody knows how, to create a hash or create a keyword, create a password that has the same hash, even though it's a different password. But nobody knows how to do that, so it's probably secure. The big value here is because even if somebody sees your database with all the hash passwords, they can't go back and make passwords that allow them to log in. Given the hash, you can't go back, so you can't. The attacker cannot create a password that will let them in. So it's best to always store the hash of the password and don't store the password itself in your database. So when somebody logs in, you take the value they gave you, you hash it, and see if it matches the hash that you calculate. Message authentication codes, or MACs, can be used to confirm that what you got comes from the stated sender. Message authentication codes not only tell you that the data hasn't been changed, but it tells you it did come from who claims to send it. So if you got a block of text and you hash it, and then you encrypt the hash, you send it to the other side gets it, and they can calculate the hash themselves, decrypt that, and compare it. If it matches, you know that the data that you received has not been changed along the way, and nobody else could have falsified it because somebody has the key, the correct key to encrypt that. And you can use whatever algorithm you like for that. You can encrypt it any way you want to. That concept is used in digital signatures. A digital signature is a means of marking email or file and say that it was created by this particular person. Again, you just take the, you make a hash, you encrypt it, and you put it on. That's, so a digital certificate, again, uses public key encryption. And typically the RSA algorithm, which again allows you to encrypt with either side. Here's the text. Let me go over my picture here. Okay. The picture just goes over the same thing you saw in the text. And of course, all the slides are on the website, on the Blackboard. You start with the plain text on the left, and you run it through your hash algorithm, and then you encrypt the result of that hash with your private key. So you're going to send something to somebody else, and you're going to encrypt it with your private. So Alice is going to send a message to Bob, which are usually the characters involved. So Alice, using Alice's private key, Alice will encrypt the message, encrypt the hash. So now we've got the hash signature. Append that to the end of the message and send it over to Bob. Bob gets it. Bob separates the hash from the text, takes that text, and he also runs it through the hash, same algorithm that Alice used. And then he decrypts the hash that he got using Alice's public key. Of course, everybody knows Alice's public key is made public. And then gets a decrypted version. Now he compares the hash that Bob calculated with the hash that he decrypted from Alice and sees if they're the same. If they are the same, then he knows the message hasn't been changed. He knows it really must have come from Alice because nobody else has Alice's private key. Anybody can have Alice's public key, but only Alice has the private key. This doesn't protect anybody from seeing the message. It just protects that, it just ensures that it came from Alice and it hasn't been changed. You can then, of course, if Alice wanted to make sure that nobody else saw the message from Bob, she could encrypt the whole thing with Bob's public key, send it, and send it by. And Bob's first step would be to decrypt it with his private key, which only he has. Digital signatures are used all over. Again, they're used for email. I've got, I'll try to remember to send everybody a digitally signed message. I use digital signatures a lot because not only do they allow you to digitally sign it, but you can use those keys to encrypt things. And so I send encrypted email because even though you think your email is private, it's not. Typically, every time I send my wife an email, I encrypt it and sign it so she can decrypt it. So not only do your email applets, programs that are on the web can be encrypted. That way you know the program hasn't been attacked. It doesn't have a virus attached to it because that would change it, and therefore that would be detected by the digital signature. And of course, it also identifies what company do it. Not only do programs, but documents, both PDF, Adobe PDF and Microsoft Word allow you to digitally sign documents. And A&T has even gotten into the 21st century. And now, if you need to sign a document, we used to have scads of paper running around, people signing their name on all sorts of paper. I used to be the department chair before Dr. Yuan was Dr. Dozier. Before Dr. Dozier, I was department chair. And I can tell you, the job consists of signing your name on paper all day long. Now we can do it electronically. Yes, now the university accepts digital signatures on online documents. Makes it a lot easier. You also, of course, sign programs, as I mentioned. Sometimes you'll see messages. This is an old message from an earlier version of Windows, but you'll see an old message where if you pop up, going to run something, it may tell you, do you want to run this? If you do, it says, it's been signed by this person. Sometimes it'll tell you it's not signed. It says, do you want to run this thing? It's not signed. And you got to make the decision that yes, you typically will run something that's signed without any problem. If you want to run something that's unsigned, you'll go, oh, wait, you want to do this? The worst case, of course, is if the digital signature is wrong. If something's happened, if it checks it because, oh, the digital signature doesn't match. Most of the time, I don't think Windows will run it. If it gets a program and it's been modified, it will not run it. If it's not signed, it gives you the option, but if it's modified, it's, nope, we're not going to do it. The digital certificates are used in this. Digital certificate is very simple. It's just a bunch of information that contains the user's public key. So you can send the public key along because typically you will use that to, well, okay. Another thing about digital certificates is that they are digitally signed. The certificate itself is signed by a certificate authority. Now, a certificate authority is just a company that sells digital certificates. It's a really nice deal. They charge you for a bunch of bits. They just have an algorithm, takes seconds to make another number, and they sell it to you for a bunch of bucks. Ones I buy for email usually last about a year and are good for, it cost about 20 bucks or something, $25. So, hey, for a couple of milliseconds of computer time, they'll send it to me for $25. If you want to get one from a server, a lot of companies will have you verify in some way that you are in fact the company that owns that server, and then they'll sell you a certificate, and they usually cost a lot more. If you look in your browser will have a list of digital certificates that it has from certificate authorities. Microsoft or Apple regular updates downloads a list of certificate authorities, public keys, and they're kept in your system. And so if you get a digital certificate, you already have the public key of that certificate authority. And since the keys are signed with the private key, here, let's look at this picture. I think it's will help explain it. Okay, Alice wants to send a message to Bob. Here's the data that she's going to send to Bob in blue on the right-hand side. And then in the purple is a checksum of the data. And that's been encrypted with Alice's private key. This is a Mac, the authentication chain. And so that's, now, of course, Bob is going to have to decrypt that with Alice's public key. Where is he going to get Alice's public key? No problem. Alice sent it along. And the certificate has Alice's public key. It also has Alice's name and a couple other things, email address. Email address is nice because email systems, when they get something that's signed, looks in their digital certificate, checks the email address in the certificate against the email address where the mail was sent, and will give you a big warning if they don't match. So anyway, Alice's public key is right there. Now, how does Bob know that that's really Alice's public key and not George's public key, where George sent the message? He encrypted it with his own private key and sent his public key, just saying it's from George. Well, because Alice's public key is encrypted, has a hash here. There's a hash of Alice's public key, and that's encrypted with the certificate authority's private key. And since you have the certificate authority's public key, it comes with Windows and the browsers, then you can then decrypt this, check that the key is correct. Now that you know that the key is correct and valid, it is in fact Alice's, you can use that to decrypt this, and then you can finally get to know that the data is valid. So you have what they call a chain of trust. chain of trust. Imagine doing this in an organization. You don't have to rely on certificate authority. Here, think about the university. You might have the chancellor might have a key. He has a public key and a private key, and only the chancellor knows the private key. So Dr. Martin's got this. Dr. Martin can then give digital certificates to all the deans, signing it with the deans with the chancellor's private key. Think of it, the chancellor knows who the deans are. He can look them in the eye, hand them a thumb drive or something, and say, "Here's your key." So he gives it to them in a secure way, knowing exactly who they are. The deans can then do the same thing for the chairs. Each dean knows who their chairs are and can give the information to the chairs, and then the chairs can do that and give information to the faculty. And that way, everybody's got a key. People who want to verify in the university who want to verify it only need to have the chancellor's public key to do this, and then they can decrypt and go down the chain and make sure it's correct. You can do this in organizations. Okay, here we have a question to see if you're awake. Start it online. There you go. And the folks in our live studio audience here can see they know the answer. Why is my phone not working? Okay. Okay. Kind of annoying. All right. What's in the digital certificate? We've got 5 more people online, so keep voting. Okay, how are we doing here in class? You ready? Put your paper in the proper orientation. Okay, the proper orientation is towards me. Yes, thank you. Oh, here. Why don't you move your hands away from to the corner? There you go. Okay. Yes, that's interesting. You didn't recognize it with your hand, your finger over it. Oh, okay. We have an A, a B, and a D. Everybody. Okay, A, B, and a D. And we have, so there's 2 A's, 3 B's, 1 C, and 1 D. Well, I guess that means nobody was paying attention at all. Oh, gosh. Okay. But remember, this is a review, folks. This is a review. Okay, the answer is the certificate contains the public key of the owner, B. Okay, a couple of people got that right. Now, you never share the private key with anybody. You assume that you have the public key of the certificate authority. And no, it's not a hash of the private key. It's because the private key is not there. You send the public key because, oh, yes, so if you see, again, the data is encrypted with the private key of the person, and then you send the person's public key along with the certificate. Public key is there. Okay. Now, let me say something about keys. Many applications will ask you for your encryption key. You're going to use a key to encrypt. How do you keep that secret? Well, one way is just ask the person, "Hey, tell me what the key is, and I'll use that to encrypt or decrypt the data." You shouldn't use the string directly. In other words, they type in a bunch of bytes. Don't use the bytes that they type directly because, well, a couple of things. One, they're not very random. I mean, think about ASCII. You have ASCII bytes on the keyboard. All the characters you type on the keyboard, the most significant bit, the 7th bit, is always 0. So right away, you know that you only have your keys are less random than you think. And then, of course, there's only so many keys on your keyboard. There's like 100 keys on the keyboard. There's not much to choose there. Not nearly as many possible combinations that actually exist. And you typically want long keys. Again, AES encryption keys are 128, 192, or 256 bits. And that means people have to type in a really long key. So the easy way to do it is you take the key that they entered and you hash it. Run it through a hash algorithm. That gives you a random bunch of bytes. And you can use that random bunch of bytes as the encryption key. Or if you want to be really secure, you can do it again. you take the string that the user entered, you run it through the hash algorithm, get a bunch of bytes, take this bunch of bytes, run it through the hash algorithm again, do that a bunch of times until you get something that you can just never go back. Remember, the hash algorithms don't go backwards. You get really messed up bunch of bits, and you use that for the encryption. Of course, if you do the same algorithm next time, you can always get back to that same key. So instead of, you shouldn't use the bytes entered directly, run them through a hash algorithm and use the hash algorithm as the encryption key. Oh, I got another clicker question. This is for Java programmers. I think some of you know I used to teach the Java class, so watch out. Oh, poll, I shot my poll here. There it goes. Okay. Hopefully you can see the question now. Oh, everybody, I think you got the answer. We've got one answer online, two answers, three answers. They're still going. Okay, that's all right. Let's turn the light to got you. Got you. Okay. We have. Let's see. Here with the online people, we've got. Well, we're going to end the poll because I think we've got five answers. Everybody's very good. Share the results. Okay. Counting the people here in the live studio audience, we have 1A, 1B, 5 C's, and 1D. Well, that's actually kind of disturbing because the answer is D. Whoever voted D, you got it. Somebody remember that in Java, strings are immutable. That is, they cannot be changed. You cannot change a Java string. If you go something like secret equals null or secret equals another string, that, remember, secret is a reference to the string in memory. And it will change the reference to the string, but the string is still there. This is important because if you read in a key into a string, you can't get rid of it in memory. It will be in memory. It's very hard to get rid of that string. That's why most of them read into an array of bytes. Because bytes you can overwrite. An array of bytes, you can change a byte. It's not immutable. Whereas strings are immutable. You can't change them. And by the way, secret.char, I'm sorry, that's not even compilable. Char returns a value, but you cannot set that solid. Yes. And of course, if C works, then A works, but okay, none of the above. Trick question, that was a question for my Java class, but no, you have to remember strings are immutable, which is important in security. If you read something into a string in Java, you cannot erase it. The key, the information will always be in memory. All right, oh, the program ends. All right, come on, review here quickly of some things to remember about cryptography. Don't ever create your own. Hey, that's a bad idea. Make sure you pick the right algorithm for the right occasion and implement it correctly using the right mode. Don't rely on security by obscurity. That just never works. You think, oh, nobody will know this. Well, you'd be surprised they figure stuff out. It doesn't work very well. Hard-coded secrets. So here's a problem I'll talk about in just a minute. Don't put the key in the code. A lot of programs do this. Well, they got to read a file, they want to encrypt it, so they'll put the encryption key in the code, and then, just to make it a little more difficult, they think, oh, exclusive OR with a constant, and so we won't see it. They look in the executable file, you won't see the key, but of course, if you run it, you can find it. Yes, there are debugging tools that allow you to run through code and step by step and look how it works. Long ago and far away, I was having a party at my house with a bunch of old computer guys. And so this is long ago, and I guess we weren't old then. Yes, once upon a time I wasn't old, but we had, it was a game people wanted to play that was on the mainframe, but it had a catch in it. They wouldn't allow you to play it from this time because people played it a lot. We didn't want to use the mainframe resources to play this silly game, which people liked a lot. So it had a check. Well, we went through it, went through the debugger, found out where it got the date and time. Oh, changed the instruction, and now it would run. So we made it, we got through it by debugging it and changing the code, which there are tools to do that. You gotta make sure you keep the information careful. Don't watch out what you put into log files. Remember that if you put something into a buffer, if you put your key into an array of characters, that's good, but don't go back and erase the array of characters. Put some zeros over it or something so it's gone out of memory. And make sure the data you store in a file database is encrypted. Here's a non-clicker question. This is not a trivial thing. Okay, so if you don't put the key in the program, how do you encrypt? How do you encrypt a file? Let's imagine you have a desktop application that wants to read and write files, read and write data to a file. It's got a file that it uses, keeps information in, and you want to keep it secret because it's kind of important for how the desktop application works. How do you keep the key? I wrote one because I wrote my own hide my keys program, so I can keep doing a program that encrypts the file, but also compresses it. But what do you do it? Well, you don't want to put it in the code. You just mentioned that's just not secure. You can always ask the user for the key. That's what I do. If you have a system with a server, you can ask the server for the key because we'll assume that the server can be secure and you can send a message to the server and ask it for the key and have it sent back. Of course, the server has to make sure that you are you. One of the things they didn't mention about TLS, Transport Layer Security, is it talked about having a certificate for the server. It also supports the concept of having a certificate for the user. Now, in general use, when you're looking at web pages, it never uses the certificate for, it doesn't require a certificate of the client. But you can say, I want to use certificate of the client. And that would, in this case, that would allow you to connect to a server in an encrypted way. And the server, you can verify the server is in fact the server can verify that you are in fact you, and then you could send you the key. Any other ideas? I'm interested because again, I wrote a program to do this. I asked the user for a key. Lacking.
Oh,
Yes.
I think there is another way. What we can do is like we can just like get the key and store it as like hash function maybe. Because
Yes.
we just need to match the key, right? So whoever the key belongs to, they know what is the keyword. So
Well,
we can just store the hash on the desktop application, and whenever we receive the particular key, we just create that hash and match it with the whatever is stored on the disk.
right. Well, you can do that to verify that this is what you were speaking. But we want to use a key to encrypt and decrypt the file. In other words, we want to be able to read and write a file. And so we need a key that we're going to use to encrypt and decrypt that file. So if you hash the key, well, yeah, I mean, you can use it as a bit. How do you have to ask you have to ask the human for it. You couldn't just keep that in your program, even if it was a hash. Yes, I mean, in my program, which does this, which encrypts the file, I ask the user for a key, then I hash it. Actually, I put it in a loop and hash it many times, and then take that really scrambled up version and use that as a key. Yeah, so I don't have any other ideas. That's an interesting problem because you can't put it in the code, even if you think, the code is hidden. Java, everything is available. There are Java utilities that will deassemble a Java, decompile a Java program. You give it a bytecode, it's a class file, and it will it'll display the Java code that makes it. It's pretty good. It can use the same file names, takes the comments out. Most of them will indent according to the standard indenting scheme. But it makes a pretty good result. So that's not as good. Okay, well, I don't know the answer to that question, but at least these ways work. Well, we know putting in the code is not good. Asking the user or asking the server are two acceptable solutions. Although asking the server requires some means of identifying yourself to the server, so the server doesn't give out the key to anybody who asks. Well, that's it for today. We're just about out of time. A reminder that Project 6 has been canceled. Project 7 has been created and will be out there on the web shortly, along with all the material for next week. And again, next week, no in-class class. It'll be online only. And that will be, again, on the 15th and the 17th. So don't be here because I won't be here. But I will be on live and online at those times. Okay, well, unless there's no further questions, that's it for today. Hopefully you all knew this stuff.
All right, thank you very much, Professor. I have one more question.
By the way,
that quiz thing that I told you about, 13 quiz, like it's still the same. We cannot see any questions or anything.
oh, okay. Let me beat on that again. Doggone, sorry, Blackboard hasn't been doing what I asked it to lately. I will try to get that quiz 13. And again, I'll do it today, or also just write the answers and put them out there. Okay.
Right. Do you want to see what kind of view we see when we see the
I'm sorry, could you repeat the question?
Do you want to see, like, we are not seeing even a questions or anything. It's just a little prompt that says what you got, like nothing else. It shows nothing else.
Okay, I'll try to get
let me just share this with you.
Okay, sure.
We can just see this thing, nothing below it, no questions, nothing. It just says the result.
Yeah, that's okay. Yeah, I clicked the box that I thought would show you everything once it's graded. I will try it again.
All right, thank you very much, Professor.
If you would send me an email to remind me, I'll make sure I get it.
All right. I will send an email.
When you're an old guy, it's a long way from here to home.
Right. Thank you very much.
Thank you very much, and I will make sure I do that. Okay.
All right.
Any other questions, issues, comments? All right. Well, have a nice weekend. The next material, which, by the way, the material for next week is assortment of security flaws. I think we're going to talk about overflow issues on Monday. That is buffer overflow, stack overflow, and integer overflow. Overflow of all flavors. So I don't know if you've had that before. I don't think it's been in this class. But in the material I got from Dr. Yuan for this next week, she mentioned those topics, and so I've expanded it. Okay, well, we'll see you next time.